This video covers modules 17 and 63 in your book. I know there's a lot of space between those, but that's where we are. We are going to look at ecological tolerance and natural disruptions to ecosystems today. Behind that. Ugh. The reality is that every species has a niche. They all have a range of tolerance, which are the limits to abiotic conditions that a species can tolerate. For example, it could be based on temperature, like some things can only grow within a certain temperature range. It could be based on salinity, sunlight, etc. So on the range, on the outskirts, both on the high and low, that is where organisms can survive. When we come in a little bit, that is where they can survive and grow. But where we want all organisms to be is where they can survive, grow, and reproduce. They are stuck in survive and grow, no reproduction. That species is going to have a grim outcome. A fundamental niche are the abiotic conditions under which a species can grow, survive, and reproduce. And a realized niche is the range of conditions where they actually live. There are two types of species. Generalists can live under a wide range of conditions, like raccoons, but there are still some specialist species that live in a small range of conditions, like a specific habitat, feed on a small group of species, and an example here would be a koala. Environmental changes can and do alter the disruption of species. Past changes in environmental conditions have led to changes in distribution. And so the example here are trees after an ice age. So we can see, the abundance and distribution of pines, spruces, and birches, throughout and to present day from the last ice age. Can we use examples from the past to determine what might happen as our planet warms? It depends on the mobility of species, sea level, average temperatures, etc. Unfortunately, environmental changes can cause species extinction. Species that cannot adapt or move will eventually become extinct. The average lifespan of a species is between 1 and 10 million years. And because we know that, over 99% of species that have ever lived on Earth are extinct. And we know that information because of the fossil record. Why do species go extinct? It could be that there is no favorable environment, or they can't move to a favorable environment. They have low mobility, or their new environment may be established with other species. And we know from the competitive exclusion principle that two species living in the same area competing for the same resources will not be able to coexist. With that, we know to date there have been 5 mass extinctions, which you can see here. Evidence suggests that we are in the 6th mass extinction, which is a book and is awesome. And we know that because our background extinction rate, or, a normal, there's always species going extinct, is 100 plus times higher than normal. So we expect that, every year, every thousands of years, whatever, some species will go extinct. We are significantly higher than that now. And we also know that because we've seen huge decreases in bird and amphibian populations. And those organisms are generally indicator species that tell us how healthy their ecosystem is. So if they're not doing so well, it's probably a bad time. We also know that CO2 concentrations have been increasing for the past 6 decades. We do need CO2 in our atmosphere. It is an important greenhouse gas that helps keep our planet warm and makes it suitable for life. So it's able to help trap heat in the atmosphere so our planet can, be suitable for us. However, excess CO2 contributes to global warming. You can see a graph from the past 6 decades to your right. This shows the millions of metric tons of CO2 that are produced by country. And then in part B, it has per capita, or per person. So even though China is the biggest producer of CO2, when we look at it per capita, it's actually one of the lowest. The US, however, is near the top of both lists. And I think this might be a case where it is not good to be, number 1 or number 2. Seems like something you probably don't want to be at the top of the list for. Our global temperatures have steadily increased since we started keeping records in the 1880s, and we are seeing a globally upward trend. But the reality is that these increases are not evenly distributed around the globe. We are losing lots of sea ice, which is habitat loss for our polar bears, and they will have nowhere to go when it is gone. This is the temperature increase around the globe. As you can see, it is very uneven. In some places, it's maybe getting a little bit cooler. Some places, it's significantly hotter. 0.2 degrees Celsius doesn't sound like a lot, but it does make a significant difference to an environment. Scientists can estimate the global temperatures and greenhouse gas concentration for, the last 500,000 years. And they do that by looking at species composition and ice core data. For species composition, they used a protist called Foraminifera, which is a small marine organism with a super hard shell. And their little tiny shells build up on the ocean floor. And different species of that protist prefer different temperature ranges. So they can tell by, okay, this type of shell is found here. It likes X degrees Celsius. So we know at this time, because of dating, that's, around what the temperature was. And so they can determine the approximate temperature and age of that area. They also use air bubbles that are trapped in ancient ice. So during compression, ice captures small air bubbles, which sample the atmosphere at the time the ice was formed. So when we extract ice cores, they can determine the time and what was present in the air bubbles. And they combine both of those things to see Earth's trend. And this is what we came up with for greenhouse gas concentrations. Our book is a little older, so this only goes to 2013, but that's a pretty dramatic increase over the last, very short amount of time. And here is what we know from ice core data and modern measurements for methane, CO2, and nitrous oxide. Very sharp increase at around the same time for all three of those that I think you might see corresponds with the Industrial Revolution. Because, are the estimations totally accurate? No, but they're not that off. They're not that bad. And here we have our CO2 and temperature. It's interesting that they increase and decrease together. And here again is temperature. Indirect measurements is our estimations, and the red bar towards the end is our actual measurements. So although Earth's temperature has changed over time, we are in a significant increase now that is explained in part by human activities, not just the Earth going through its cycle. So what happens as our Earth's condition change? Organisms either adapt, move, or die. The choice is theirs. Well, honestly, I think it might be ours.